Okay, so I mentioned in class the other day I was not able to finish discussing this topic, but we're going to go over average rate of change. I planned on making this video on my iPad, but I was still having some issues with connectivity. I thought I had fixed them, but apparently I cannot at the moment get that to work. So I decided to just do a direct video here on the whiteboard. So average rate of change, okay, is by definition how much a function changes in value over a particular interval. So I'll just start with the setup. You can draw a set of coordinate axes. Okay, so you can go ahead and draw in your x and y axis, and I'll just draw some arbitrary function f. Okay, so this is the graph of a function f right here. And what you're going to do is you want to know, okay, over a period or over an interval, okay, on average, how much do function values either increase or decrease per unit increase in the independent variable, okay? So what I did, I wrote this at the end of class. Okay, so what I can do is I can pick two particular x values. For now, I'll just call them a and b. And what that's going to do is that's going to correspond to 2 points on the graph of my function. Okay, so you'd plug in a and you'd plug in b, and that's going to give you two outputs in particular. Okay, so if I plug a into the function, I get an output over here on the y-axis f of a, and if I plug in b, the height of that second point would be the output f of b. Okay, and these points right here would have coordinates. I'll just use an arrow here. So this point has coordinates a comma f of a, and this point up here has coordinates b comma f of b. Okay, and hopefully everybody can see that well enough. Okay, hopefully there's not too much glare on the whiteboard. Okay. And then the next thing you're going to do is you're going to consider the line between these 2 points on the graph. Okay, so I'll draw a line. Let me make sure I have a marker that's vivid. And another purple one. Hopefully this one has. Okay, great. Okay. So there's the line between those 2 points on the graph of f. Okay. And I will go ahead and define the average rate of change now. So definition, the average rate of change of f on the interval from a to b, okay, or from x equals a to x equals b, is going to precisely be the slope of that line between those 2 points. Okay, so sorry, let me step out of the way. Okay, and it's going to be denoted this way. I'll just write m for slope, and the subscript SEC stands for secant. Okay, so any line between 2 points on a graph is called a secant line, and the average rate of change is just the slope of the line going through those 2 points. Okay, now if my coordinates are a f of a and b f of b, we know that the slope of a line between 2 points is the difference between the y coordinates, or the outputs, f of b minus f of a, divided by the difference of the inputs b minus a. Okay. So that would be the definition of the average rate of change, and again, hopefully everybody can see that well enough. Okay. So we'll go ahead and go through some examples, but that's basically the general idea. Okay, so keep in mind that when you're doing average rate of change, it's over an interval on the x-axis. Okay, in this case, I've just chosen a and b to represent those x values, or x coordinates. Okay, and again, what you would do is that's going to correspond to 2 points on the graph at a and b. And the average rate of change would be the slope of the secant line through those 2 points. Okay. Now there's 2 ways you can do this. On the homework, you should see this in 2 different ways. So on one hand, you will be given functions graphically, and you will just have to read the graph to find the average rate of change, or you could be given the algebraic expression for the function and have to do it algebraically without aid of a graph. So I think I'll do the algebraic point of view first, and then we'll go ahead and I'll show you how to do it graphically. Okay, so maybe an example here is I'm going to say find the average rate of change of f of x equals, and I'll just do, say, a quadratic function here. I'll do, say, x squared plus 3x. Okay, and we're going to do this on the interval from, let's see, we can go ahead and do, let's do the interval from 1 to 3. Okay. Okay. So the way this works is the average rate of change, okay, or the slope of the secant line, is going to equal, now it's going to be the quotient. Now these are your values of x on the x-axis. So you're only looking at the graph from x equals 1 to x equals 3. Okay. And what you'll do is you'll take the difference in outputs. Okay. You'll do f of 3 minus f of 1 over 3 minus 1. Okay. And using your function, I can go ahead and plug these values in. F of 3, okay, is going to be what I obtain when I plug 3 into my function for x. So the first one would be 3 squared plus 3 times 3. Okay, so that's f of 3. Notice again I've replaced each x value here with the value of positive 3. And then I will subtract f of 1. Now f of 1 has 2 terms, but f of 1 is going to be 1 squared plus 3 times 1. Okay, and then of course in the denominator you're just going to take the difference in your x coordinates, which would be 3 minus 1. Okay, and you can go ahead and simplify this. So I'll just go ahead, 3 squared is 9, plus another 9 would give me 18. Okay, that would be f of 3 minus, and then f of 1 is 1 squared plus 3 times 1, which is going to give you positive 4, and then you would divide by 3 minus 1, which equals positive 2. Okay. Now 18 minus 4 is 14, divided by 2, and I will get an average rate of change of positive 7. Okay. So now, technically I should probably give you an interpretation of this. What this means is that on the interval from 1 to 3, okay, this means that on average the function is going to be increasing by 7 units every time I move 1 unit to the right. Okay, so if I increase the value of x from 1 to 2, on average the function is going to increase, or the graph is going to rise by 7 units. Okay, if I increase another unit, if I go from x equals 2 to x equals 3, again, I can expect on average or approximately that the function value is going to increase by 7, or the graph is going to rise by 7 units. Okay, so this is basically saying on the interval from 1 to 3, every time I go to the right 1 unit, the graph is going to go up by approximately 7 units. Okay. All right. So basically, again, just one more time, what's happening is if you want average rate of change of any function on an interval, okay, what you're going to do is you're going to take the difference in function values between 1 and 3. So that's how I got f of 3 minus f of 1, and you would just plug 3 and 1 into the function and take the difference. And in the denominator, you're just taking the difference in the x coordinates, which is 3 minus 1. You work this out and you get 7. So on average, on the interval from 1 to 3, the function values are increasing by 7 every time I increase the x value by 1 unit. Okay. Now, what I have left to do now is to do this graphically. So on the one hand, you can be given a function algebraically, and you can just directly compute the average rate of change using the expression given by the function. The other thing you can do, okay, is now this time, what if I give you the graph of a function? Okay, and I'll just make something up right here. Again, say I have some graph of a function. Let's say that I've got 2 points that correspond to x equals 2 and say x equals 5. Okay, and let's say that, I don't know, this point right here has a height of positive 1, and let's say this point right here has a height of 3 units. Okay. Now, again, I'll at least write the coordinates of these 2 points up here. The first point has coordinates 2, 1, and the second point on the graph has coordinates 5, 3. Okay, and again, hopefully everybody can read those coordinates down there. And if I say find the average rate of change of f on the interval from 2 to 5. Okay, let's get rid of this quarter right here. There we go. Okay, so the average rate of change of f on the interval from 2 to 5. And just visually, that average rate of change is going to be the slope of the line between those 2 points. Okay. So now the average rate of change is going to equal, now first I'll write it down in terms of function notation. It's going to be f of 5 minus f of 2. Okay, so the difference in outputs between between x equals 2 and x equals 5. And in the denominator you should have 5 minus 2. Now, f of 5 and f of 2, those are just the y coordinates that correspond to x equals 5 and 2. Okay, so these 2 points right here, okay, so when x is equal to 5, the output is 3. Okay, so f of 5 equals 3, and then you're going to subtract f of 2, which is the y coordinate, positive 1, and then you're going to divide by 5 minus 2. And when you work that out, you should get a value of 2/3. Okay. Now, looking at the graph, what that basically means then is on average, if I start at x equals 2, anytime I increase my x value by 1 unit, that means that you should expect the y coordinate to increase by 2/3. And again, that's just a change on average. Calculus, the idea in calculus is you don't really want to look for average rates of change in calculus. You want to look for instantaneous rates of change. Now, so this line through these 2 points is called a secant line. Average rates of change are slopes of secant lines. When you get to calculus, you're going to learn about something called a tangent line to a graph. And instantaneous rates of change would be slopes of tangent lines. If you're interested, or you want a little bit of a preview of that, or you want to understand that further, I would be happy to talk with any of you. The best you can do though with algebra or pre-calculus is you can compute average rates of change. So it's not until calculus where you probably are going to investigate further and look at instantaneous rates of change. Okay. So now what I want to do is, if you remember in section 1, we talked about the difference quotient, and there is a connection between the difference quotient and average rates of change. So, what I'm going to do is I'm going to draw that same picture as before. Okay, I'm going to just draw a set of coordinate axes, x and y axis. So there's my y-axis, there's my x-axis, and I'm just going to draw any old function again. Now, this time what you're going to do is this time I'm just going to use the notation x. And what I'm going to do is I'm going to add some quantity to that x value. Okay. So I start at x, and I'm going to add a quantity. Okay, the width of this interval is going to be denoted by delta x. Okay, so I don't know if you've seen this in other classes before, but the symbol delta, or that triangle up here, that's this notation that means change in. So when I write delta x, that's how much x is changed by, or the change in x. Okay, so I'm starting at x and adding delta x to obtain x plus delta x. You'd still come up to the graph. It's going to correspond to 2 points. Okay, the first one has coordinates. I guess I'll write these on the side in just a second, but let me actually first say that again, the average rate of change is going to be the slope of the secant line between those 2 points. Okay. So now, those 2 points in question up there, the first point right here, since the input is x, that first point is going to have coordinates x comma f of x. Okay, so x comma f of x is that first point on the graph. The second point on the graph is going to have coordinates x plus delta x is going to be the input, and f of x plus delta x is going to be the output. Okay, and you'll see now if I do the slope of the secant line, okay, it's going to be the difference in y coordinates. So f of x plus delta x minus the y coordinate of the first point, f of x. And in the denominator, okay, you're going to have x plus delta x minus x, which is ultimately just going to be this distance right here. Okay, so you're just dividing by the change in x. Okay. And furthermore, if you let h equal delta x, okay, and I just rewrite this in terms of h, I would get f of x plus h minus f of x over h, and that is precisely the formula for the difference quotient. Okay, so when you are finding difference quotients in section 1.1, you are actually finding equations for slopes of secant lines. So those are arbitrary expressions for slopes of secant lines, depending on how much you increase x by, which in this case is delta x, or back there you were using h. Okay, so let me know if you have questions. Again, those are the 2 things you should be expected to do. You should be able to find average rate of change given a function as an algebraic expression, okay, over intervals. The other thing you should be able to do is pick off average rate of change using a graph. And again, it's really over an interval. It's the simplest way to say it is it's just the difference in outputs, or y coordinates, divided by the difference in inputs. Okay, or in other words, the slope of a secant line. So I hope everybody has a good night. Stay safe out there. Drive carefully. It's probably icy. The road conditions aren't good, so stay safe. I hope to see you all in class tomorrow, and thanks for tuning in. Hopefully the board doesn't have too much glare and everybody can read it, but take care for now. Thank you.